So welcome back to the channel and welcome to Excel Island, where the goal and objective is to learn and master Python over the next 100 days. Today is day 50. We are half or 50% to the 100 learning journey. So we're just going to continue from where we stopped on day 49, which is our introduction to statistics. We are on the 7th course out of the 9 courses in the career track, our data analyst in Python career track on the Datacamp platform. So the 7th course is all about introduction to statistics in Python, rather, and we are on the chapter 3 of this course, which contains chapter 4. So each courses in this whole career track usually contains 3 or 4 chapters. So as usual, so we're on the third chapter of Introduction to Statistics, and we'll be looking at the concept of the Poisson distribution. So we learned all about different types of statistics from chapter 1. We've looked at random numbers of probability and different distribution types like continuous distribution, discrete distribution, and uniform distribution, and normal distribution. So we've covered quite a lot. So if you want to catch up on the previous live stream, the previous lesson, I'll encourage you to go to the live stream tab on Excel Island YouTube channel so you can catch up on the various lessons so far. So we started all the way from day 1, the basics of Python, rather. So I'll just continue from where we stopped and start sharing my screen. So today we'll be looking at, we continue from chapter 3 because it actually contains a lot of lesson. Let me just share my screen really quick here. So it usually contains a lot of lessons. So the goal is to break it down and learn every day, at least 1 hour daily. So I'll cover the concept bit by bit. So get it now. So we'll be looking at the Poisson distribution today. Then probably we'll complete this section today. Move on to the correlation and experimental design of the chapter 4 in the next day, which is the next live stream. So just continue. So before I continue, I'll just go back here and open up so this is the data set we'll be using so far for this chapter. You can see the 7th course, Introduction to Statistics, since beginning of chapter 1, chapter 2, and chapter 3 of the course. I'll just open this chapter 3 or Jupyter notebook here. So this data set, the meal deals data set, that's what we'll be using for chapter 3. So this food consumption and world happiness was used for chapter 1. So there's a link under the description so you can download this data set and every other data set we've been working with so far. So you can also practice your Python skills with me. So without further introduction, let's continue from here. So let's look at the Poisson distribution.
In this video, we'll talk about another probability distribution called the Poisson distribution. Before we talk about probability, let's define a Poisson process. A Poisson process is a process where events appear to happen at a certain rate, but completely at random. For example, the number of animals adopted from an animal shelter each week is a Poisson process. We may know that on average there are 8 adoptions per week, but this number can differ randomly. Other examples would be the number of people arriving at a restaurant each hour, or the number of earthquakes per year in California. The time unit, like hours, weeks, or years, is irrelevant as long as it's consistent. The Poisson distribution describes the probability of some number of events happening over a fixed period of time. We can use the Poisson distribution to calculate the probability of at least 5 animals getting adopted in a week, the probability of 12 people arriving in a restaurant in an hour, or the probability of fewer than 20 earthquakes in California in a year. The Poisson distribution is described by a value called lambda, which represents the average number of events per time period. In the animal shelter example, this would be the average number of adoptions per week, which is 8. This value is also the expected value of the distribution. The Poisson distribution with lambda equals 8 looks like this. Notice that it's a discrete distribution since we're counting events, and 7 and 8 are the most likely number of adoptions to happen in a week. Lambda changes the shape of the distribution, so Poisson distribution with lambda equals 1 in blue looks quite different than a Poisson distribution with lambda equals 8 in green. But no matter what, the distribution's peak is always at its lambda value. Given that the average number of adoptions per week is 8, What's the probability of 5 adoptions in a week? Just like the other probability distributions, we can import Poisson from scipy.stats. We'll use the Poisson.pmf function, passing 5 as the first argument and 8 as the second argument to indicate the distribution's mean. This gives us about 9%. To get the probability that 5 or fewer adoptions will happen in a week, use the Poisson.cdf function, passing in the same numbers. This gives us about 20%. Just like the other probability functions you've learned about so far, take 1 minus the less than or equal to 5 probability to get the probability of more than 5 adoptions. There's an 81% chance that more than 5 adoptions will occur. If the average number of adoptions rises to 10 per week, there will be a 93% chance that more than 5 adoptions will occur. Just like other distributions, we can take samples from Poisson distributions using Poisson.rvs. Here, we'll simulate 10 different weeks at the animal shelter. In one week, there are 14 adoptions, but only 6 in another. Just like other distributions, the sampling distribution of sample means of a Poisson distribution looks normal with a large number of samples. Time to practice taking Poisson probabilities.
Okay, let's look at challenges in Poisson probabilities. So in our data set here, we've learned all about different libraries. Okay, we've learned all about uniform, binom, and norm from scipy.stats. So another one we could import is from scipy.stats imports Poisson distribution. If you run the code, good. So we learned all about these libraries in Python. Now it's time to put it to good use. Okay, so let's see what we need to cover here. It's saying identifying lambda. Now that you've learned about the Poisson distribution, you know that its shape is described by a value called lambda. In this exercise, you will match histograms to lambda values. Match each Poisson distribution to its lambda value. Okay, lambda 1, lambda 4, and lambda 8. Drag the items into the correct brackets. Okay, we look at this distribution. The peak is on lambda 8 here. It's probably 7 and 8. Let's give it a shot here. While this peak here is on lambda 4, 3 and 4, but we could go for 4. While the next one should be on lambda 1. Let's see. We nailed it. So we learned that the peak, the lambda is the distribution's peak. You can see. So marvelous matching. The Poisson distribution is a family of distribution, just like the uniform binomial and normal distribution. Interesting. So tracking lead response. So tracking lead responses. So your company uses sales software to keep track of new sales leads. It organizes them into a queue so that anyone can follow up on one when they have a bit of free time. Since the number of lead responses is a countable outcome over a period of time, so this scenario corresponds to a Poisson distribution. On average, Amir responds to 4 leads each day. So in this exercise, you'll calculate the probability of Amir responding to different number of leads. So we need to import our Poisson. Import, okay, let's go back a little bit. From scipy dot stats import from scipy.stats import Poisson. Yeah, we got that. Probability of 5 responses. So import Poisson from scipy.stats and calculate the probability that Amir responds to 5 leads. Amir responds to 5 leads in a day, given that he responds to an average of 4. So on average, he responds to 4. You get it now. So 5 leads in a day. So that would be percent dot PMF. So 5 leads. The average is 5. Current probability that may respond to 5 leads. So 5 leads and average of 4 per week. Let's run the code. Cool, let's start the session. So probability is 15%. Interesting. So Amil co-workers respond to an average of 5.5 leads per day. What is the probability that she answers 5 leads in a day? Okay, hold up, let me copy this. So I like using, okay, hold up. I want to copy this. And also give it a shot here. So I just read this line of code and try it out in Jupyter Notebook too. I see that we are getting the same results. So if I submit, so Amil co-workers responds to an average of 5.5 leads per day. What is the probability that she answers 5 leads in a day? Amil co-workers. Now ask that what is the probability that she answers 5 leads in a day? Okay, that can be. Let's see that. Probability of 5 responses in a day. An average of 5.5. Okay. I'm going to use same percent dot PMF. Since the response to 5.5 per day, so it's probably that answer 5 leads per day. Let's see. That is 0. Ooh, that's not correct. Use percent dot PMF. Yes. Check your call. Did you correctly specify the first argument expected? 5, but you got 5.5. Okay. Oh, sorry. This is supposed to be 5. Then 5.5. Probability is 17%. Okay. 17%. So what's the probability that I make responses to 2 or fewer leads per day? Like less than 2. So we are looking at less than 2. Less than. So it is supposed to be less than 2 in a day, which is 2 or less. I'm going to use percent.cdf for this scenario. .cdf for this scenario. So, but what's the average? What's probably the mean response to 2 or fewer leads per day? Since the average per week, so definitely average per week is 4, right? The average per week for me is 5. Per week is 4. Okay, per week is 5. So less than 2 should give us less, that is 0.98%. Interesting. How do I copy this? So the probability that I make response to 2 or fewer leads per day is 98% probability. Okay. Oh, we use CDF, of course. Oh, I'm missing. So you know that the average per week is 5 leads. So this has to be 2. I'm missing up the numbers. It has to be 5. That is 12%. Probability should be low then. So I'm missing up the numbers. So which argument should come first? That is 12%. Let me take a look again. Okay, so what's probably that Amir responds to 2 or fewer leads per day? So the first argument is 2. What about the first argument here? It's 5. Oh, because this is CDF. So I'll use CDF. It is PMF. So you need to know the difference between the two. This is PMF and this is CDF. Probably that you expect less than 2 leads is, oh, I'm doing a mistake. It's supposed to be 2. It's supposed to be 5 here. I think it's the CDF. That is 12%. Oh, expected 4. The average per week is what? 4. Oh, oh, oh. Mean that Amir spends on average of 4 per week. Okay, yeah. That is 23%. This has to be 23%. This has to be 4. Since Amir average per week is, consider Amir's average per week here is 4. That's why we are putting 4 there. We know that information. So this one say what is probability that Amir responds to more than 10 leads in a day? That'll be 1 minus, so 1 minus CDF. 1 minus minus person dot CDF. That should be 10. Then the average per week is 4. That we know here. That is 0. That is less than, that's even low. That responds to 10. 10 is not even visible. That probability is 0%. That responds to 10 leads per day. Perfect. So perfect percent probability. Note that if you provide %.pmf or %.cdf with a non-integer, it throws an error since percent distribution only applies to integers. Interesting. So I want to copy this line of code here. So probably that it responds to above 10 is 0%, 0% probability. Okay, so let's move on. Oh, don't worry about that. So we've done 50 days. Have we done 50 days letting go journey? I think we've done that before. Mm. So more probability distribution. So what other probability distribution do you want to look at here? Distribution dragging and dropping, modeling time between leads. So let's see what we have. Oh, there's something called T distribution. Okay, let's see what we need to learn here.
In this lesson, we'll discuss a few other probability distributions. The first distribution is the exponential distribution, which represents the probability of a certain time passing between Poisson events. We can use the exponential distribution to predict, for example, the probability of more than 1 day between adoptions, the probability of fewer than 10 minutes between restaurant arrivals, and the probability of 6 to 8 months passing between earthquakes. Just like the Poisson distribution, the time unit doesn't matter as long as it's consistent. The exponential distribution uses the same lambda value, which represents the rate, that the Poisson distribution does. Note that lambda and rate mean the same value in this context. It's also continuous, unlike the Poisson distribution, since it represents time. For example, let's say that one customer service ticket is created every 2 minutes. We can rephrase this so it's in terms of a time interval of 1 minute, so half a ticket is created each minute. We'll use 0.5 as the lambda value. The exponential distribution with a rate of 1/2 looks like this. The rate affects the shape of the distribution and how steeply it declines. Recall that lambda is the expected value of the Poisson distribution, which measures frequency in terms of rate or number of events. In our customer service ticket example, this means that the expected number of requests per minute is 0.5. The exponential distribution measures frequency in terms of time between events. The expected value of the exponential distribution can be calculated by taking 1 divided by lambda. In our example, the expected time between requests is 1 over 1/2, which is 2. So there's an average of 2 minutes between requests. Similar to other continuous distributions, we can use expon.cdf to calculate probabilities. The probability of waiting less than 1 minute for a new request is calculated using expon.cdf, passing in 1 followed by a 2, which gives us about a 40% chance. Note that we're passing in 2, not the lambda value, which is 0.5. The probability of waiting more than 4 minutes can be found using 1 minus expon.cdf of 4, 2, giving a 13% chance. Finally, the probability of waiting between 1 and 4 minutes can be found by taking expon.cdf of 4 and subtracting expon.cdf of 1. There's a 50% chance you'll wait between 1 and 4 minutes. The next distribution is the t-distribution, which is also sometimes called student's t-distribution. Its shape is similar to the normal distribution, but not quite the same. If we compare the normal distribution in blue with the t-distribution with 1 degree of freedom in orange, the t-distribution's tails are thicker. This means that in a t-distribution, observations are more likely to fall further from the mean. The t-distribution has a parameter called degrees of freedom, which affects the thickness of the distribution's tails. Lower degrees of freedom results in thicker tails and a higher standard deviation. As the number of degrees of freedom increases, the distribution looks more and more like the normal distribution. The last distribution we'll discuss is the log normal distribution. Variables that follow a log normal distribution have a logarithm that is normally distributed. This results in distributions that are skewed, unlike the normal distribution. There are lots of real-world examples that follow this distribution, such as the length of chess games, blood pressure in adults, and the number of hospitalizations in the 2003 SARS outbreak. In addition to the 3 in this video, there are lots of other probability distributions that are out of the scope of this course, but you can learn about in other Datacamp courses. For now, it's time to practice the distributions you've learned so far.
So I've covered a lot of distributions so far, and that is quite a lot. So that means there are probably more distributions. Come on, just for Python alone. So let's see what we have here. Say distribution, dragging, and dropping. So by this point, you've learned about many different probability distributions that can be difficult to remember, which is which. So in this exercise, you practice distinguishing between distributions and identifying the distribution that best matches different scenarios. So match each situation to the distribution that best models it. Amount of time until someone pays off their loan. Amount of time. You can't track the time. Can you track the time? That should be a fixed. There should be a fixed time for that. If I'm not sure, let's see. Amount of time. Amount of time until someone pays off their loan. Even though we're only looking at the Poisson, exponential, and binomial, we didn't look at the normal distribution. So amount of time someone pays off their loan, I'll probably go for since time, but since the time will be fixed, so you have to guess. I'll go for binomial. Amount of time until next customer makes a purchase. Next customer makes the purchase. Let's go for exponential. Number of products sold per week. Mhm. Okay, let's switch this one here. Less amount of time some pays of their load follows exponential distribution. Since exponential distribution is used to model time between independent events that happen. Okay. Let's see amount of time, number of products sold per week. You say it is number of since it is an independent variable, it says it varies. So you can't guess which one it is. Let's go for this. Number of people from a group of 30 that passes driving test. Hmm. Number of people from a group. Okay, let's see. Number of customers that enters each store each hour. Hmm. Okay, let's take a look again. There's a number of so I'm looking between this number of customers that enter a store each hour. It's probably a binomial or an exponential distribution. Let's give it a shot. I'll still go for a position here. There's a number of people in a group that pass their driving test. Let's see. Ooh, I missed this up. That means this is not amount of time until next customer makes a purchase. Okay, let's see. Voila. So time until someone makes a purchase. Now that we've practiced distribution, it's time to focus on the exponential distribution. Okay. So modeling time between leads. That is the exponential distribution. So to further, let's look at this. So to further evaluate a mail's performance, you want to know how much time it takes him to respond to a lead after he opens it. On average, he responds to one lead every 2.5 hours. In this exercise, you will calculate probabilities of different numbers of time passing between a mail receiving a lead and sending a response. So okay. So import from SciPy. Import expon. Okay, import expon from SciPy the start. So what is the probability it takes a mail less than an hour to respond to a lead? Let's import expon. It's going to be from scipy.start dot start import expon. So let's import expon. I'll just go up a little bit here and add it to our library of, so our list of libraries I've learned all about. So we're working with exponential distribution for that. So it says import, what is the probability a meal that it takes a meal less than an hour to respond to leads. Let's see. So a probability of less than an hour, that will be equal to expon dot dot cdf an hour. So probability is 1 hour and the scale is 2. Our scale, what's our scale rate here? With it responds to, okay, say on average it responds to one lead every 2.5 hours. So 2.5, let's see. 2.5. So that's what's the probability it takes a meal less than an hour to respond to a lead. Okay. Let's run the code. That is 32%. Are we correct? Yeah, we know that. So on average, the scale is 2.5 hours to respond to one lead. So now, so what is the probability that it takes a meal less than an hour to respond to a lead? So the calculation is 32%, 5.3%. Next one says, what is the, okay, let's submit. So what is the probability, okay, have I done this? What is the probability it takes a meal more than 4 hours to respond to a lead? More than 4 hours. And expon.cdf, open brackets, more than 4 hours. So 4, and the scale is 2.5 is the scale. Oh, my code is not coming up. Let me just reload the page. I have to reload this page. I don't know what's happening. It's not coming up. Come on. Why is it taking time to load? I have it here. So let me just copy this line of code here. So instead of this is 1 and our scale, okay, this will be 4, more than 4 hours. That is 79% or probably 80%. Oh, we didn't get that. Well, probably it takes, I mean, more than 4 hours. Okay, more than 4 hours. That should be 1 minus, 1 minus probability of that. That is 20%. Now we nailed it. So if you run the code, that is 20%. So now say what probably it takes a mail between, what's probably it takes a mail 3 to 4 hours to respond to a lead. Like between 3 to 4 hours to respond to a lead. That is 3 to 4 hours. That means 3 minus 4. If I copy, let me just copy this line of code here to save time. I just copy this. Subtract it from 4. So this should be 3 minus 4. Probability of minus 4. Which one is the highest? 3 to 4 hours. I think the highest should come first. So this should be 4. And this should be 3. 3 to 4 hours. Wow. Let me just reload this page again. Trying to run the code now. This is not active. So I have to copy this and reload the page again. Let me put it here and see it in action. Oh, minus. My minus is missing something. Hold up, hold up. So incomplete input. I'm having multiple prints here. Print this minus this. But print is covering this. I could as well just get rid of the print, which is confusing. That's your S spawn and S spawn. So it's okay like this. Let's leave the shots. But that is 0.9%. 0.09%. So this is what we need here. Probability is 0.09. This is still loading. Come on. The probability of a mail, it takes a mail 3 to 4 hours to respond to a lead is 0.09% probability. Oh, what was all this? Sometimes you have no control over the network. You just have to bear it. It's probably the page because my streaming is quite strong. I could I could track my streaming bitrate from here. So we are to run the code, submit this. What am I missing? Okay, what is missing here? The second one, right? 1 minus this, okay. Then the last one is this one here. That is 0.09%. So we nailed it. So excellent exponential computation. So there's only about 20% chance if you take Camille more than 4 hours to respond. So it's pretty speedy in his response. So 20% chance, like we see here, that more than 4 hours to respond to his response, to his leads. Oh, good. Finally, we've nailed this probability and distributions and the central limit theorem lesson so far. Interesting. So which statement is not true regarding the T distribution? So a T distribution has thicker tails than the normal distribution. That is true. So it says a T distribution with higher degrees of freedom resembles the normal distribution. A T distribution does not resemble the normal distribution. We've established that. The number of degrees of freedom affect the distribution variance. The T distribution is skewed. Oh, I'm confused between these two. I remember these two perfectly well from the lesson. You get it now. So if you pay attention very well. But between these two, the T distribution is skewed. I'll probably go for the number of degrees of freedom affect the distribution variance. It's skewed. Probably this or this. Mm. Number of degrees of freedom. What is degree of freedom? Was that mentioned? I'll go for this. T distribution is skewed aspect. Terrific. The T distribution is not skewed, just like normal distribution, but it does have thicker tails and higher variance than the normal distribution. Okay, see, we know that. So the number of degrees of freedom affect the distribution variance. Okay, so that'll be the end of this chapter 3. So next we are moving to what do we have here? The concept of correlation and experimental design. So we continue from here on day 51. So hopefully we are going to be completing the whole lessons in the career track, the whole curriculum, the whole projects in the career track before the 100. So I show you a quick peep into what the whole career track looks like real quick. So we have a couple of projects after this to take it to solve, just to practice and hone our skills. If I go to the career track section real quick here, we are 50%, at least 53% above to complete the whole career track. So what do you have here? So we still have a couple of projects. After the introduction to statistics, we have introduction to data visualization with Seaborn. Then we have a couple of projects, skill assessments. Then we have exploratory data analysis in Python. We have another project. We have sampling in Python, hypothesis testing in Python, and we have the last project. So I look forward to this project and challenges also. So that'll be the end of the live stream for today. So if you enjoyed this Python learning journey with me, do well to give this live stream a thumbs up, hit that subscribe button whenever you come across this video, and make sure to download the data sets under the YouTube description so you can also practice and hone your Python skills and become a Pythonista. As usual, I'll see you in the next video on the channel or on the next live stream. Let's get back to work. Have a wonderful rest of the day.